let's just do it for the simplest solution that we can find. So so a monochromatic plane wave. And to keep things simple, we're just going to, by choice, we're going to propagate this along the z-axis. So what I mean by this is that I will have so it's going to be a plane wave that is, it doesn't depend on x and y. It's just like one value for a given z, and it propagates in the z direction. So my E is going to be a function of only z and t, not of x and y. And it's going to be some constant vector once again that I'll have to specify. We don't know anything about this vector here. But now the dependence is just going to be e to the I k z minus omega t. I can write this more cleanly. Okay, I mean, everybody's used to writing these complex exponentials for real fields. Have you done that before? You understand the agreement that the actual physical field is just like the real part of that thing. We're just using the exponential because it's easy to multiply and whatnot. Okay, so the physical field is just the real part of that thing here. So then a cosine, you know, I'd fit it with my conditions. Okay, so so that would be the thing. So what do we need to impose? Actually, let's also say that my B has the same kind of form, ZT. This is B0, e to the I kz minus omega t. Okay, so what do we have to fulfill? We have to fulfill Maxwell's equations. So first of all, I need the divergence of E to be equal to 0. So what is the divergence of E? Well, essentially, there's only one spatial dependence here, which is along Z. Yeah? So divergence of E is ddx of Ex plus ddy of Ey plus ddz of Ez. But here, in this combination here, there's no X and there's no Y. Therefore, that doesn't contribute anything. But there is a Z. So if I want this to be 0, I need the E0 vector's Z component to be equal to 0. Everybody see this? So this is dx of Ex plus dy of Ey plus dz of Ez. Okay? And here, this E0, you can view as a vector, which is E0 x along x hat plus E0 y along y hat plus E0 z along z hat. Okay? And this component here multiplies everybody, but there's no x and no y. Okay, so dx of Ex, well, there's no x dependence here. These are just constants, so there's nothing. So this is 0. This same thing here, it's 0. But the dz of Ez is just the E0z with now Ik e to the I kz minus omega t. Okay, so that's the only thing that's left. And the only way that I can make this whole thing 0 is if I put the prefactor to 0. Okay? Am I like explaining too much here? Confusing you, or is it okay? So this condition here, Gauss's law in vacuum, means that if I'm propagating along Z, then my electric field has no component along Z. So therefore, the E field is transverse to the propagation direction. Okay? So similarly, div B is equal to 0, the no-name law tells us that B is also transverse. Same thing. There's no Z component in the B. Okay? Therefore, if my wave's going this way, my E and B fields have to be in the plane perpendicular to the direction of propagation. I don't know anything about the E and B fields besides that for now, but they have to be in that plane, both of them. Okay? Coming from Gauss and from no-name. We really have to baptize this law. Yes. Okay. Now, we can go further. We can then solve the other equations that that we have. So, for example, Faraday's law. So what does Faraday tell us? It tells us that the curl of E has to be equal to minus dB dt. So what does that tell us? So let's do it in components, right? So maybe just looking back at our maybe I can just rewrite them here so we have them. So now we have E of Z and T is just this E0 e to the I kz minus omega t. Okay, and then the B of ZT again has this B0 e to the I kz minus omega t. Okay, so let's just see what that tells us. Let's take the x component. So what's the curl of E? Yeah, so you remember, right? So x hat, y hat, z hat, dx, dy, dz, ex, ey, ez, determinant. So the x component is dy ez minus dz ey. But the Ez we just showed was 0. So this is 0. Okay. And I've got minus dz of Ey. Ey is E0 component y with the e to the I kz minus omega t. Right, but now I'm taking the z derivative. This is just a constant. So I'm just getting that this is minus I k with E y. Right? So when I take the time derivative of B, I get that this would, so the x component here, so that's one thing. So what I need is minus I k ey has to be equal to minus the time derivative of the x component of B. Okay, the time derivative here gives me minus I omega. Yeah, so this becomes I omega and then Bx. Okay. So what that means is that my coefficients, so I can just remove the I. So I've got minus k with the E0 component along y has to be equal to omega times the B0 component along x. Okay, that's what Faraday in the x direction tells me. I can do the same in the in now the y component. So what's going to happen here? I'll have dx ez minus dz ex. So the ez vanishes, so I just get minus dz ex now has to be equal to the dy. So again, it's the same kind of absolutely the same kind of equation that I've got here. So I've got the extra minus sign, right? Because I'm now doing the y. So I instead of having minus d, I get plus dz ex. So it's the same equation here, but I've got the plus sign here instead of the minus sign. So I just get then that k times E0 x has to be equal to B0 y. Okay, so that's for the y component of this. So if you just put these together, you can just look at the components, and there's a kind of good way of writing it. You can just say that the B0 vector here is proportional to the cross product between the E0 and the Z, with a coefficient here that is just this ratio K over omega that I have here. Okay, so what does that equation tell you? So this Z here was the propagation direction. Okay, what this is telling you is that there's the propagation direction. The electric field is perpendicular to that direction, and the magnetic field is perpendicular to both. Okay, so, and if you just like use Faraday's two components here, you have determined now the full magnetic field if you know what the direction of the electric field is. Okay, so that's the kind of idea. So that's how we write a plane wave. So for a general plane wave, yeah, again, monochromatic. You all know what monochromatic means, right? So single color, namely single frequency. So now let's just get away from Z, but now it works for any direction that I might have. So I will have an electric field here as a function of space and time, which I will write as some constant vector E0 with a monochromatic dependency, namely a single frequency, but now a general direction K, which earlier was just Z, but now I'm leaving this completely general. Single frequency here. My B would then be given by solving the Faraday equation here in precisely the same way, where now this is a general direction here for the vector. So this would be and omega is equal to ck. So this is just 1 over c with k vector hat dotted into E of RT. Okay. Right, and actually, what I should let me just rewrite this a tiny bit to correspond to the notation I've used in the notes, because I've put an n hat vector here. So this is just now some constant amplitude, but this is the propagation direction. No, sorry, it's the polarization direction. The direction of the electrical field. And what you have is that there's a transversality condition that tells us that the propagation direction, so this is really the propagation direction, the propagation direction is transverse to the polarization. Okay, so this is transversality condition. Okay. Can you read? Propagation direction, choice of a direction for the electrical field, given that direction and size of the electrical field, the magnetic field is completely fixed. Okay? And of course, this is just valid for any direction that you might have. So the K vector is just the direction in which you're going. The N vector is the direction in which your electric field is pointing. Okay? And then you have that that thing here. Of course, with the understanding that the actual physical fields would be, say, the real part of that object here. Okay? Is that okay? Have you actually done this in your first course a bit with your thing? So maybe you need like a refresher of this, but this should also like look very similar to what you've done. Okay. Now going back to our original question, what's the most general solution that I could imagine for my electromagnetic fields here? Well, you see, I can choose any direction K that I want. For any K, I can choose the polarization. And for given direction and polarization, now I still have, you know, a lot of choices, because the only constraint that I have is that omega has to be C times K. Yeah, but I can choose the omega, I get different Ks for a given direction. So that's the space of possible electromagnetic fields is given by this kind of multiple infinity of choosing the direction, then choosing the polarization, then choosing the actual, you know, length of your K. Right? Very importantly, don't think that the kind of sine and cosine is the only thing that you can have as a solution to these equations. In fact, arguably, physically, they're not so great, because this object here has an infinite extent. There's no spatial suppression of any of this here. But that's not really how you view physics, right? You kind of view things as moving, you know, relatively localized, moving away. The point about these wave equations is that any function f of kr minus omega t is a solution. Okay? So do it the complicated way. Fine. So we've got essentially this combination here. I can decompose an arbitrary field like that, maybe one that's even localized in space, into its Fourier series, its Fourier transform. Yeah? Each component of this transform being one of these monochromatic plane waves. But actually, I could say, well, you know, I've got a hump. So the only requirement of the wave equation is that there's a correspondence between the time dependence and the spatial dependence. The shape actually doesn't matter. It doesn't have to be sinusoidal. It doesn't have to be cosine. It can be any shape that you want. It can be a modulated thing. It can be a hump. It can be a box. Provided the thing moves at the right velocity, it will solve the wave equation. So in general, when you kind of write the general solution to many of these things, you can actually afford to just say, well, you know, let's just write this shape, or maybe we've got a thing which is not a purely monochromatic wave, but it looks like a wave of high intensity with a small tail that's just moving. In fact, there's a great example of that in Purcell-Morin that you can look at. I think it's, yeah, geez, which section? Good question. 9.6, 9.7, something like that, where he discusses the waves. So that's an important thing, right? So you are not dictated to have sinusoidal waves. It can be an arbitrary shape, provided the dependence is k dot r minus omega t. And then when you take the derivatives, you see, you'll automatically get that the thing is fulfilled because the Laplacian minus mu 0 epsilon 0 second time derivative of k dot r minus omega t, yeah, in arbitrary powers, that always vanishes. Okay, so you can put any function in there. That's kind of an important thing. Okay, so yeah, maybe a couple of final comments on this. So the Poynting vector, now that we have this thing, you see what I need to do is 1 over mu 0 E cross B. But you see, if I do E crossed into B, I'm going to get again the propagation direction, right? Because both E and B are perpendicular to the propagation direction. Now I'm taking the cross product of all of these. So the Poynting vector for a monochromatic plane wave is just something that goes along the propagation direction and carries at the speed of light an energy density U. Okay, where this U here is like the density that we've seen before, right? So essentially we had epsilon 0 over 2 E squared plus 1 over 2 mu 0 B squared. But here, for this monochromatic plane wave, the B is proportional to the E. And essentially, the size of this thing is the same as the size of this one. And it just becomes epsilon 0 E squared. And when you do some kind of time averaging for this, you end up with this, this energy density that you have here. Okay, so you see the physical interpretation of this equation is super simple, because what does this thing is? Poynting vector is energy flow per unit area per unit of time. So it's going in that direction. It's carrying an energy density U at the speed of light. Okay, that's what this this equation tells you. The momentum this momentum G is just 1 over c squared, the S, U over c k hat. And again, the kind of same reasonings. So for an electromagnetic wave, you know, the momentum is the energy over c. So then essentially you have to do a 1 over c squared this one in order to get the momentum here. Everything's proportional to each other for these particular waves. Okay, so these are like simple basic facts about these monochromatic plane waves that we will build upon when we first discuss matter, but then also discuss how waves interact with interfaces and whatnot. Okay, so you had seen the waves before, but hopefully you hadn't seen pointing before. Maybe you had seen pointing before. I'd be very disappointed, but that's where it is. Yeah. Okay, so then that would be it for today. I will let you digest that. Next time, we do Maxwell's equations in matter and then plunge into electromagnetic waves in matter and build on that to really do a lot of physics in these things.